So hello everybody, I'm Joan Calafell from CASE, and today I'm going to explain how we have combined artificial intelligence and computational fluid dynamics to create a tool that has to be, must help us in improving the air quality in our cities. So probably most of us, when we think in Barcelona, this is the image that comes up to our mind. But unfortunately, Barcelona is not always like this. So depending on the meteorological conditions we find, we can have something a picture like this. Almost 4,000 people or lives could be saved in Barcelona metropolitan area if the World Health Organization recommendations were followed. So it's obvious that we have to take some measures in order to solve this problem. So having real-time predictions would help us in taking immediate measures that would help lower the peak concentration pollutions in some areas. For instance, what we could do is just making the drivers to drive slower, or just closing the traffic in certain areas. Another option would be, for instance, providing this information to Google Maps, for instance, in order to provide or to propose alternative routes avoiding the most affected areas. Well, we already have one tool, a very powerful one, which is Computational Fluid Dynamics, in order to make this kind of predictions. So the problem of Computational Fluid Dynamics is that they are very expensive, and it takes really long time to reach a solution, because the pre-processing step it's quite long, and then you have to submit the simulation to the Mare Nostrum queue, that some of you know that this could take some time. So if you have somebody in front of the computer waiting for a fast solution because he has to take immediate measures, he can do like this. So as we don't want to end up like our colleague, we have to think in alternative ways to get fast predictions. That's why we resort to artificial intelligence. So we wanted to leverage their capabilities to generate fast predictions for taking these measures. So what we have done is generating a vast data set in order to allow the neural network to learn the underlying physics of the problem, so that the neural network can offer us these predictions in working time with just a fraction of the cost, so just in a few seconds. So what we have done is selecting 30 different urban areas in Europe, and we have run up to more than 500 different scenarios, combining different meteorological conditions and pollution emission scenarios. So these are the geometry. So there were some samples of the simulations we have introduced in the neural network in order to make the train. So the final target is just making the neural network to learn the physics behind the problem, so it can reproduce, or it can generate the velocity fields and the pollution concentration maps for any geometry, even if this one was not present in training time. So we want our neural network to create new data, okay? So basically, the way it works is we provide the geometry for which we want to know the predictions, and we give the meteorological conditions at that time, basically the wind direction. So in the first layer, we obtain the wind fields on this area. So in a second step, what we do is just we provide the traffic intensity. So combining both data, it can generate the final step, which is the pollution concentration maps, in which we can identify very easily which are the most problematic and where we have the peak concentrations of pollution. Okay, this is a real example of the output of the neural network. This is a trial we have done in El Prat de Llobregat, so where we deployed a huge network of sensors in order to make a validation of the model. So at the end, our objective is just having or trying to the most clear atmosphere in our city for the longest time as possible. So to finish, I just wanted to comment that this project has won the HPC Innovation Excellence Award from Hyperion Research, so just a few weeks ago. And finally, I just want to thank all the people that has made possible this project, especially to FFR EuroHPC initiative for funding the project. Our industrial partner, Better Maps, with which we have made a very nice collaboration, and also my colleagues at the larger scale computational fluid dynamics group, so basically Samuel Gomez and Uriol Lemkul, and also the rest of CAST, especially to Guillaume Rousseau for his help in making the data set possible. Okay, that's it. Thank you.
Thank you.